that this surface integral is equal to 2a vector into v, where a vector is a constant vector and v is the volume enclosed by the closed surface S. So v be the volume enclosed by the closed surface S. So for this we have to take U be the region enclosed by S. We have to suppose this first, and then later on we need to apply the Gauss Divergence Theorem over here. So let U be the region enclosed by S. We need to get this result, right? For that, let's take a vector, that is your constant vector, to be equal to a1i vector plus a2j vector plus a3k vector. And our vector, we know that it is xi vector plus yj vector plus zk vector. To evaluate this surface integral, let's find out first this vector. So the cross product of a vector and r vector. So writing here I vector, j vector and k vector. And now writing here the components of a vector, that is a1, a2, a3. And then writing the components of r vector, that is x, y, z. Evaluating this, we get I vector into, this is a2z minus a3y minus j vector. So this is a1z minus a3x plus k vector. This is a1y minus a2x. Now to take the cross product of n vector with this a cross r vector. Now if I use the Gauss's Divergence Theorem, and now if I use the second form of Gauss's Divergence Theorem for this surface integral, so that will be equal to the volume integral of, because we have taken U be the region enclosed by S, so writing here U. So this is curl of this vector a cross r vector du, right? So now we have to take the curl of this a cross r vector. So for this, now writing the components of cross product of a vector and r vector, which we have just evaluated over here, right? So the first component is a2z minus a3y. The second component is a1z minus a3x, because minus is multiplied outside of this bracket. So taking this inside and we get a3x minus a1z. And the third component is a1y minus a2x. Okay, let's find this. So this is I vector, partial derivative with respect to y of a1y minus a2x minus partial derivative with respect to z of a3x minus a1z minus j vector, partial derivative with respect to x of a1y minus a2x minus partial derivative with respect to z of a2z minus a3y plus k vector, partial derivative with respect to x of a3x minus a1z minus partial derivative with respect to y of a2z minus a3y. Very fine. So this is equal to I vector. Derivating this with respect to y, we get a1. That's it. Minus derivating this with respect to z, we get minus a1. But there is minus sign outside of this bracket, so this becomes plus a1. Minus j vector. Derivating this with respect to x, we get minus a2. Derivating this with respect to z, we get minus a2 plus k vector. Derivating this with respect to x, we get a3 minus Derivating this with respect to y, we get minus a3. But there is negative sign, so this becomes plus a3. Managing this negative sign inside the bracket, we get plus a2, which can be written as twice of a1i vector plus a2j vector plus a3k vector. And that is equal to twice of this is nothing but your constant a vector, right? Marking this as 1. And now from the given surface integral, what we are having? It is the surface integral of n vector cross product with a vector cross r vector ds. So by Gauss's second divergence theorem, this integral is equal to the volume integral of curl of this cross product of a vector and r vector. So this is equal to the volume integral of, okay, what is the curl of a vector cross r vector? 2 times a vector du. This is your constant vector, so I'm taking this outside of this integral. So this is twice of a vector volume integral du. And because u is a region enclosed by the surface S and v be the volume enclosed by the surface S, so this total integral is v. So here I'm writing v. That is the volume enclosed by the closed surface S, right? U is a region enclosed by the surface S and V is the volume enclosed by the surface S. So we have shown that the given surface integral is equal to 2 times a vector into V. Okay, thank you. Stay blessed.